University. This is talk about full covering results and intersection theorems and symmetric groups via hypercontractivity. It's a long title. And this is mentioned based on joint works with my amazing advisors, Nathan Keller and Ron Lifshitz. Cool. So the plan of the talk is just to talk about two problems that may seem unrelated for a first glance. The first problem is about squares of conjugacy classes, and the other problem is an intersection problem in SM. And then we'll formulate the problems in a language, and they may seem very similar, and it will be natural to apply the same techniques to them. And we'll talk about the proofs. Okay, so let's start. So we start with the conjugacy class in SM, and we define the square of the conjugacy class as the set of all the products of two conjugates. And we ask for which conjugacy classes a squared is equal to all the symmetric. So what's the answer for that?
Definitely not of the identity.
Okay.
Has to be at least square root of factorial.
Okay. Yeah. Any other directions? Okay, so I actually tricked you. So in A squared, all the elements are even permutations. So it can't be equal to all of SM. So that's not the problem. We ask whether A squared is equal to AN, or for which conjugacy classes A squared is equal to AN. Okay. So the first result was due to Gleason, and he showed that every even permutation is a product of two n cycles. And this proof was analytic, not like an explicit construction. And there has been found an explicit construction only in 2004, like some algorithm to represent each permutation. So there is some depth to this result. And later it was generalized to other special cases, but nothing really general, until Larsen and Shalev proved that every permutation, every conjugacy class that has bounded number of cycles satisfied that the square of it is all over here. And this bound on the number of cycles is very natural, because the number of cycles in the permutation is closely related to the size of the conjugacy class. So that connects to what you said. And notice that the number of cycles in the random permutation is logarithmic. So they really proved the theorem for almost all the conjugacy classes. And shortly after, they also improved their own result, and they replaced the 1/128 by a quarter minus epsilon. And that was what was known for the last 15 years. And we managed to improve the quarter in the exponent by 2/5. And that is probably still very far from being tight. I think that the result should hold up to all n cycles. Any questions about this problem? Okay. So let's move on to the next one. So we now talk about intersection problems. And the formula for intersection problems is start with a family of sets usually, and you ask each two sets in this family to have some condition on the intersection. So for the classical setting, you work with subsets of size k of 1 to n, and you ask, like the basic problem is the Erdős Sós problem, which asks every two sets to intersect. And unless there is some redundancy in the parameters, the extremal example is a dictator, which is just all the sets that contain a specific element. And there is the t-intersecting variant, which asks every two sets to intersect on at least t elements. And sometimes the extremal example is the T-unverate, which is an intersection of T dictators, but it is not always the extremal example, and this was completely solved by Alsweden and Hachdarian. Now there is the forbidden intersection problem, which asks every two sets in the family to not intersect on exactly T-1 elements. And notice that if a family is T-intersecting, then it is T-1 intersection 3. So, like every example for the T-intersecting family is an example for the T-1 intersecting family. And it might be surprising, but actually, Ellis, Keller, and Lifshitz showed that for a wide range of parameters, they are exactly the same. They have the extremal example is exactly the same. So that's nice. But we came to talk about permutations. So now we have all of these problems in the permutation language. So we define the intersection of two permutations as all of the indices which they agree on. And now we have there's a Frankel problem, which is the Erdős Sós variant. And you ask every two permutations to intersect. And the extremal example here is also dictatorship. And you have the T-intersecting variant. And the extremal example here is sometimes a T-unverate, sometimes not. This problem is not solved for every DNA, although there were advances in the last few years. And we will be interested in the T-1 intersection, forbidden T-1 intersection problem. So let's talk about the works. So, okay, we defined it, but let's define it again. A T-unverate of permutations is the set of all the permutations that sends I1 to J1 up to IT to JT. And Ellis and Lifshitz showed that the T-unverate is indeed the maximal T-1 intersection free family of permutations for T which is smaller than T log n over log n. And the n minus T factorial is just the size of the T-unverate. And it was later improved by Kupavskii and Zakharov to O tilde of n to the third. And we improved it to C square root of n divided by log n. And there are directions for going maybe up to n over polylog n. Okay, so that's for the improvement. Are there any questions about that? Okay, so let's reformulate them. We need a few definitions for that. So a Cayley graph is a graph on a group. The vertices are the group elements, and there is an edge between two groups elements if they differ by an element from the generating set of the Cayley graph. And another definition is an independent set in a graph, which is just a set of vertices with no edges between them. So let's combine these two definitions and ask when a set is independent in a Cayley graph, and the answer is if B times B inverse is not intersecting with the generating set of the Cayley graph. And this is quite easy to see just from the definition of an edge. You can multiply by G to inverse and see it. And notice that if B is also a conjugacy class, then B is equal to B inverse. Sigma and sigma inverse has the same cycle structure. So here we can replace B times B inverse by B squared if B is also a conjugacy class. And notice that if A is also a conjugacy class, then the intersection of B squared and A is either the empty set or it contains at least one element, and then also all of its conjugates. So this will be all of A. So we have two options, either A or now let's reformulate our problems. So reminder, the first problem is about a square of a conjugacy class. So now we have the following observation, which says that the square of a conjugacy class is all of an, if and only if the conjugacy class is not an independent set in the Cayley graph that is generated by tau Sn, another conjugacy class for every conjugacy class tau Sn. So let's say that again, symbols. So sigma Sn squared is equal to an if and only if it is not an independent set in a Cayley graph for each Cayley graph that is generated by an even conjugacy class. Okay, so let's see why this is true. So b squared is equal to an if and only if the intersection of b squared with the conjugacy class is like the whole conjugacy class. And this happens if and only if the intersection is not empty. That's what we saw on the previous slide. And this is equivalent to say that B is not an independent set in the Cayley graph. That's also from the previous slide. Okay. So I think it's a useful way to think about our problems. So now instead of trying to figure out what is sigma Sn squared, we just try to bound independent set in the Cayley graph. Okay. So now we have the other problem, and we say that a family is T-1 intersection free if and only if it is independent in this Cayley graph, which is generated by all the permutations that have exactly T-1 fixed. So why is that true? So two permutations, the intersection of two permutations is exactly the flex points of sigma tau inverse. So that's the definition of intersection of permutations. So we have that B is T-1 intersecting free if and only if B times B inverse, which is this, is not intersecting with the set of permutations that have T-1 fixed points. And yeah, and that was the criteria for an independent set in a Cayley graph. Cool. Any questions about that? Okay, so what we did so far, we had a theorem about the largest independent set in the forbidden T-1 fixed point Cayley graph, and we had a theorem about the largest independent set that is also a conjugacy class in the Cayley graph that is generated by other conjugacy class. And now I think it's natural to ignore this conjugacy class requirement and just ask what is the largest independent set in this Cayley graph. It's a natural question. And we also have a theorem for that, which, okay, it is very long, but it says that the largest independent set has density n to the minus delta t if n is large enough compared to t. And you can see it as a generalization of the forbidden intersection problem, actually, because the Cayley graph that is generated by a permutation, by a conjugacy class with t fixed points, is actually a subgraph of the forbidden t fixed points Cayley graph. Yeah, so you can take this Cayley graph, you remove a lot of the edges, you just take one conjugacy class, and you ask what happened to the largest independent set here. It turns out that if before it was of size roughly n to the minus t, sorry, not size, measure, and now you get measure n to the minus delta t. So, like, not a lot larger. And Sm. Okay, so now let's talk about the proofs. So that is your last chance to ask about the problems itself. Okay, so let's talk about an analytic approach to the problems. Okay, so notice that if we start with an independent set and do a random walk to a random neighbor, then we'll end outside of the independent set. That's clear? So if we define the random walk operator, which is that for n f and x just averages f on the neighbors of x, we have that if f is an indicator of an independent set, we have that okay, the dot product of tf and f is the expectation on all the edges of y, f of y times f of x. That's just the definition of t. And now we can see that for f, which is an indicator of an independent set, we can't have that x and y are both in the independent set. So f must be 0 on at least one of them, so this expectation is 0. So actually, tf and f are okay, has inner product 0. So we want to show that if the independent set is large, that can happen. And we do that by understanding the eigenvalues and the eigenvectors. And in our case, it is a convolution with a class function. So it will be useful. And now things are going to get more technical. So if you are interested in the technicality, you can dive into the details. If not, you can just see the big picture. Okay, so from representation theory, we know that this inner product of Tf and F can be written as a sum on a lambda chi, which are the eigenvalues of T, times the two norm of F equals chi squared, which are the projections of F on the eigenspaces. So, like, what is happening here? Like, the operator has eigenspaces which correspond to isotypic components of L2 of Sm, which correspond to the irreducible representations or the characters of Sm. And if you don't know a lot about that, you can just believe me that those are the eigenspaces and eigenvalues, and that you can write f equals chi like this convolution. Okay, so we have this sum, and we can just take the trivial character out of this sum. And now the plan is to show that the inner product of Tf and F is greater than 0, that Tf and F are actually correlated. Yeah, and how we're going to show that? We're going to show that the contribution of the trivial character outweighs all of the other characters. So we want to show this inequality. And if we show this inequality, it means that F is not an indicator of an independent set. Okay, so now we have a clear plan. So it turns out that these eigenvalues are sometimes very easy to compute or to bound, and they, for a lot of Cayley graphs, they decay really fast with the dimension of the character. So now the classical way to use that is using the Hoffman bound, which means bounding all the eigenvalues by the maximal one. And then we can bound this sum by the maximal eigenvalue other than the trivial one, times this sum of f equals chi 2 norm squared. And now we have that this is the expectation of f squared, which is f, because f is an indicator, minus the expectation of f squared. This is like a Parseval or Shalev. And if this thing is smaller than the expectation, then it is not an indicator of an independent set. So we have a bound on the expectation of f. We get this bound. But okay, so this is the classical way, but we do something a bit different. So instead of bounding only the eigenvalues by the maximal eigenvalue, we also want to bound these projections. So we want to show that f is not very correlated with the eigenspaces that correspond to low dimension characters. So that's the plan. And if you look at this picture, so the plan is going to show that the eigenvalues decay fast with the dimension, and that the two norm of f equals chi squared divided by e of f squared grow up slowly with the dimension. So they start low and grow up slowly. And then for low dimension characters, the multiplication of this, the blue line by the green line is going to be small because lambda chi are small. And when the dimension grows, it is going to be small because the two norm of f equals chi is going to be small. And when the dimension grows, it's going to be small because the lambda chi is small. Yeah, so was that clear? Okay. So now we have the plan, so we need to bound the eigenvalues and the two norm of f equals chi. So let's start with the blue thing. So so we said the goal is bounding two norm of f equals chi from above. And the intuition is that f equals chi is somewhat like the degree decomposition in the Boolean hypercube. Okay. And then in the Boolean hypercube, we have the level D inequality, which surprisingly just bound what we need. The two norm of f equals d squared divided by e of f squared. Okay, so it seems promising, and we can think about the level D inequality as if a Boolean function has a low expectation, then it is concentrated on the high degrees. So with this intuition in mind, we can see that in Sn it's not the case. So okay, maybe someone has an example. For a function that is of low degree but has small expectation.
Dictators or?
Yeah, okay, exactly. So a dictator is of expectation 1 over n and is of degree 1. So yeah, so we don't really have a chance of proving a variant of the level D inequality. But okay, so we don't have a chance for things that are correlated with dictators. But for global functions, we do have a chance. So, okay, so let's have a reminder that the D unrelated is a set of permutations of the form all the permutations that sends I1 to J1 up to ID to JD. And now the plan, I should say, the plan is to define a family of functions that have a chance to satisfy the level D inequality. And so we need a few definitions. So for a D unrelated, for a function a D unrelated, we can restrict the function to the unrelated, and we call the two norm f I goes to j by the two norm with respect to the unrelated space. And now we can define a global function, which is f is global if the restriction to each the unrelated doesn't bump the measure by more than r to the I. that doesn't bound the so we think about R as some constant, or maybe n to the delta. Okay. And we say that the set is global if its indicator function is global. Okay. So is the dictator global? Okay, why not? Okay, yeah, so when you restrict it to the 1 goes to 3, the measure goes up. And is AM global? Okay, so actually AM has a measure of half. So when you restrict it, it can't be more than it can go up more than 2. So yeah, it is global. And it also turns out that if you have a large conjugacy class, it is global. So maybe I'll not go over the history of hypercontractivity for global functions because I just did it, right? And we just go into the theorem that we use, which is by Kivash and Lifshitz, which says that, okay, it gives us the level D inequality for global functions in the symmetric group. So it bounds the 2 norm of f equals d squared by the expectation of f squared times, okay, this thing which is slightly worse than the hypercube that we won't care about. And we actually use this variant of the level D inequality, which bounds the 2 norm of f equals chi squared by the expectation of f squared and times the dimension of the character to the beta plus epsilon. So beta is related to the density of the function, and epsilon is some small constant that is related to the globalness. So, and it is not completely clear why this theorem implies this corollary, but you just have to use some bounds for presentation in the symmetric groups. Okay, so we had the hypercontractivity for global functions. So let's recall our plan. How much time do I have?
Let's see, you have 30 or 40 minutes.
Okay. Okay, so let's go back to our plan. We show that the blue line goes up, starts slow and go up slowly. That's this inequality. And we want to show that the lambda chi are going to decay fast. Okay. So actually the eigenvalues can be computed pretty straightforward, and for this operator, like okay, for the Cayley graph that is generated by conjugacy class, the eigenvalues are chi of tau divided by chi of 1. And Larsen and Shalev in the paper from 2008 had upper bounds on the character values, which are chi of tau smaller than chi of 1 to the alpha. For alpha, which depends on the obviously on the conjugacy class, but if the conjugacy class has at most t fixed points, we can bound alpha by this ugly thing. Okay, so now we have also bounds on the eigenvalues. So we can prove this following theorem, which says with a lot of words that the global independent sets in this Cayley graph have small density. And this is the small density. Okay, so do you see the proof already? Okay, so let's recall that the proof is like everything we just said. We are going to have the dot product of TF and F, and we want to show that this is greater than 0, and we do that by bounding this sum, which is the sum of all the characters except the trivial ones, and show that this sum is smaller than the expectation of F squared. That was like the plan all along. And now we know that the eigenvalues are chi of tau divided by chi of 1. And we know that the 2 norm of F equals chi squared is bounded by the level D inequality, which gives us this bound. And here the half minus log n of T divided by 2, that's just where we use the assumption of the density. So we assumed F has a density larger than this. And we'll get a contradiction. So now we use Larsen and Shalev's bound on chi of tau divided by chi of 1, which gives us this thing, and it cancels out with this thing, which gives us this ugly sum, and the sum is on all the dimensions of the irreducible characters to the minus sum s, and this sum is actually called the Witten zeta function, and it was proven by Liebeck and Shalev that it goes to 0 when epsilon is constant and goes to infinity. So this is smaller than 1, large enough n. Okay, so there were a lot of technical stuff, but I hope that at least the plan was clear. Any questions?
So in order to improve your result of whatever you want T, right, be large and large. You need improvement on the Larsen and Shalev, right?
Okay, so notice that this result is like on the largest global independent set in this scale graph. So I think no one asked like what the largest global independent set is, because usually like it's a new concept, global sets. So but the bound itself is pretty good, like sub-exponential. So but yeah, if you want to improve it, you can either improve the Larsen and Shalev bound or the hypercontractivity, but I think it's pretty tight. Okay, but we aren't finished yet because we just bounded the global independent sets. We will need to bound the general ones. So now we have to complete the proofs using this bound. And the plan is going to be like have some combinatoric argument that says you start with a set, with a general set, or in some cases a conjugacy class, and you construct from it a global set. And somehow this global set is going to be also independent in the Cayley graph, and then you're going to get some contradiction. So that's the plan. I do want to show some details because usually people skip that stuff. So, okay, so now we are going to prove one of the 3 theorems, which just bound the largest independent set in the Cayley graph we just talked about. Okay, so what is going to be the proof? We start with an independent set of high measure, and we need to bound the size of, okay, we know how to bound the size of a global independent set, so we have to use that somehow. So starting from our original independent set, we find the global restriction, which means a restriction which is global with respect to the new space. and it is quite easy to find such a restriction. And we can also assume without loss of generality that I is equal to J. So we have a restriction that looks something like take 1 to 1, 2 to 2, up to K to K. And since this restriction is global and is of high measure, it is not independent in the K graph that is generated by a permutation, by a conjugacy class. So which conjugacy class do we take? We take the conjugacy class that is derived from the original one by taking out I fixed points. And now, if bi goes to I is not independent, it means that there are permutations that differ by tau 0, or by conjugate of tau 0. So we can just add, like, take these two permutations, add the same I fixed points to them, and before they differed by tau 0, so now after you add the same I fixed points to them, they will differ by tau. And when you added the I fixed points, you got permutations from B itself. And they differ by a conjugate of tau, which completes the proof. So there were some details in it, but I hope that the general idea is clear. And okay, so that solves one of the problems. So we go to the maybe more interesting one, which is a variable is equal to an. Okay, so now we want to bound independent sets in the same K graph, but we also assume that they are conjugates. That they are conjugacy classes. So we have an independent set, which is also a conjugacy class, and we want to bound its side. And the idea is the same idea, except here stuff is a little bit more nice, because actually f equals chi for f, which is an indicator of conjugacy class, is chi of sigma times chi times constant. So okay, there are a lot of equations here, but what they say is that the inner product of Tf and f can be written like this: E of f squared, which we had before, plus E of f squared times the sum of chi sigma squared, which comes from f equals chi, times chi tau divided by chi of 1, which is the eigenvalue of this operator. Okay, so now we want to bound this. Okay, maybe let's say we want to bound this sum and show that it is smaller than 1. And we have the Larsen and Shalev bound, which bounds us chi of sigma and chi of tau from above by chi 1 to the alpha of sigma or alpha of tau, which gives us this thing, which is what we already had a name for that, which is the width and zeta function, and we know that it goes to 0. So this is small. So you may ask yourself, okay, why aren't we done yet? Like we had the bound on chi of sigma and chi of tau. We had the bound on this sum. What else do you need? So actually, the bound on alpha and sigma and alpha of tau do depend on the cycle structure of sigma and tau. And while you can ask sigma to maybe not have many small cycles, you can't ask that about tau, because tau was just a general permutation in AN. So you can't finish by just this argument, and we need to find like a combinatorial way to cancel out small cycles in sigma and tau, because that's actually the stuff that that is bothering us for this bound. Okay, and that is actually what Larsen and Shalev already did in their paper. They found the cancellation method, which is just a way to remove cycles from both sigma and tau. And what we did differently is we proposed a different method which allows us to remove more small cycles, but it also removes paths, which are non-closed cycles. So what do I mean by that? Actually, removing cycle is like doing a restriction of 1 goes to 2, 2 goes to 1. And then you remove 2 cycles. And when I say we remove path, it means we do a restriction that is not a cycle. Okay. So as a result, we actually lose the fact that sigma is a conjugacy class, but we manage to save the fact that tau is a conjugacy class. So the Cayley graph is still is generated by a conjugacy class. And we end up with a restriction of a conjugacy class, which we have to prove that is not an independent set inside the Cayley graph of Sn and tau 0 of Sn, because we did the restriction. Okay, so can somebody guess like what's the plan now? So again, we have a restriction of a conjugacy class, and we have to show that okay, we can say it's of a high measure maybe, and you have to show that it is not an independent set inside the Cayley graph. Okay, so I'll tell you, the plan is simple. We just show that the restriction is global. So if you start with a large conjugacy class and you take a restriction, it turns out that the restriction is global. And then we can use our previous theorem about global independent sets inside this Cayley graph. Okay, so that's like that completes 2 out of 3 problems. So let's go back to the last one. And now our Cayley graph is different. So the Cayley graph is the Cayley graph that is generated by all of the permutations with t-1 fixed points. And okay, we have to bound the eigenvalues, and we can think about random walk in the graph this way. You take a permutation and you choose t-1 coordinates to keep the permutation the same, and all of the other coordinates you change it randomly. So it does remind us of the discrete noise operator, which changes almost all the coordinates, so rho is pretty small. But we know that the eigenvalues of that are smaller, t over n to the d. And okay, we also, like, that's the intuition that we also managed to prove that. So yeah, it looks like we have the same plan, like let's find some global restriction, blah blah blah. And so it does look promising, but it turns out that it is not that simple, and like, okay, we can prove that global independent sets are small, but from that to get to general independent sets, it was not that easy. Like actually, some ugly stuff are going on there. And it turns out that if we just disregard this all algebraic approach and representation theory sum, and just treat it as like some pseudo-random subset inside Z mod n to the n, and work with the Fourier there, we have much simpler proof and probably tighter bounds. So actually, we don't have a proof that uses all the stuff that I told you. I do think there should be one, but yeah, we just disregarded it. Okay.
Sorry, so Do you use global hypercontractivity now or no?
So we used the variant that was proved by Keller, Lifshitz, and Marcus for product spaces, but not for SN. Okay. Any questions about that? Okay. So let's summarize. We had a theorem about the score of a conjugacy class with not that many cycles, and we said that it is equal to all of AM. We had a theorem about the T-1 intersection free family of permutations. And we had a theorem about the largest independent set in the Cayley graph that is generated by a conjugacy class. And we had a combination of techniques: global hypercontractivity, representation theory, and combinatorial arguments. Okay, so what's next? So you can try to improve the bounds we had already on the size of the conjugacy class or the relation of T and N. You can ask the same questions for other groups, like what happens if you take a large conjugacy class in SLN? Does the square of it is equal to all of SLN? And another meta question, which I don't think we can really answer, but maybe have some convincing intuition, is that is the forbidden intersection problem, or like generally intersection problems in SN, really has anything to do with the algebraic structure of SN, or they always just work for a pseudo-random family of Z mod n to the n. Yeah, that's it.